So if we follow all the intermediate steps one by one, then in the first step, the sodium atom is converted to gaseous state. This change requires energy which is provided by the enthalpy of sublimation. Note that the sublimation is defined as the direct conversion of a solid into a gas at constant temperature and pressure. And the enthalpy of sublimation is the change in enthalpy which occurs when 1 mole of a substance sublimes at a specified temperature and pressure. In the second step, gaseous sodium atom is converted to gaseous sodium ion. The ionization energy or the ionization potential energy is required for this process. We can define the ionization energy as the energy required to remove an electron from the neutral atom. In the fourth step, chlorine atom is converted into a chloride ion by accepting an electron. The energy required for this process is equal to the electron affinity of chlorine. The electron affinity of an element can be defined as the energy given off when a neutral atom in the gas phase gains an extra electron to form a negatively charged ion. In the fifth step, gaseous ions, that is sodium ion and chloride ion, combine to form solid sodium chloride crystal, and the energy evolved in this step is known as lattice energy. As we discussed earlier, lattice energy is the energy evolved when gaseous ions combine together to form 1 mole of the solid ionic compound. According to Hess law, the overall energy change in a process depends only on the initial and final states and not on the route taken. So we can say that the enthalpy of formation that we discussed in the very first equation is the sum total of the various enthalpies involved in the intermediate states. I hope you remember this was the first equation we discussed, in which a solid sodium atom and chlorine in its gaseous state combine to form sodium chloride crystals. And the enthalpy change in this reaction is the enthalpy of formation. So as per Hess law, enthalpy of formation is the sum total of enthalpy of sublimation of sodium, ionization energy of sodium, half of the dissociation enthalpy of chlorine, electron affinity of chlorine, and lattice energy of sodium chloride. Now let's try to solve few simple questions based on the concepts that we have just discussed in this chapter. The first question: for two ionic solids, calcium oxide and potassium iodide, which will have higher lattice energy? Let's recall that according to Coulomb's law, the force of attraction between ions is directly proportional to the charges on the ions. In case of calcium oxide, the charges on the ions are +2 and -2, and in case of potassium iodide, the charges are +1 on potassium ion and -1 on iodide ion. So it's pretty simple that the force of attraction between the ions of calcium and oxygen, that is calcium ion and oxide ion, will be much greater in the lattice of calcium oxide, and therefore it is going to have higher lattice energy. It is also supported by the experimental facts which show that the lattice energy of calcium oxide is much higher than that of potassium iodide. Second question: which of the following choices will not favor the formation of an ionic compound AB? First is high ionization energy of A, second is high electron affinity of B, C is high lattice energy of AB. If we can recall the various intermediate steps we discussed in the Born-Haber cycle depicting the formation of sodium chloride, ionization energy was the energy that was to be supplied when the atom A was converted into a positive ion, A+. Similarly, electron affinity of B was the energy released when B gained an electron to form a negatively charged ion. Lattice energy was also the energy released when A plus ion and B minus ion combined to form the ionic compound AB in its solid state. A plus and B minus are in their gaseous states. So ionization energy is the energy which is to be supplied among these three. In case ionization energy is very high, then the energy barrier post may be so high that it may not be overcome by the sum of the energy released in the other intermediate steps. In that case, ionic compound AB may not be formed. So our answer will be A, that is high ionization energy of A. Third question, which of the following solvents is best for ionic compounds? The number mentioned in the parenthesis depicts the dielectric constant of that solvent. The four solvents given are acetic acid with dielectric constant 6.2, acetone with dielectric constant 21, formic acid with dielectric constant 58, and chloroform with dielectric constant 4.81. By Coulomb's law, the force of attraction between the ions was inversely proportional to the dielectric constant of the medium. We studied it while discussing the solubility of ionic compounds. So, higher the dielectric constant of the solvent, lower will be the force of attraction between the ions, and much easier will be the breaking away of the ions into the solvent. That is, their solubility will be high. So that solvent in which the ionic compounds are most soluble should be such in which its ions feel the least amount of attraction. For that, the dielectric constant will have highest possible value. In the given solvents, formic acid has the highest dielectric constant. So among these four solvents, formic acid will be most suitable for dissolving ionic compounds. Next question. Reaction enthalpy of which of the following reactions will be equal to the lattice energy of sodium chloride? Now, if we remember the definition of lattice energy was the energy involved when gaseous ions combined to form 1 mole of solid ionic compound. Among the given choices, choice D says that gaseous sodium ion combines with gaseous chloride ion to form solid sodium chloride. So the enthalpy of this reaction will be equal to the lattice energy of sodium chloride. So our answer is D.